today we're starting chapter 20, which is all on carboxylic acid derivatives. And there's a lot of resonance today. So our good friend resonance comes back, not just drawing resonance structures, but actually using resonance structures to tell us something about the structure. And so actually being able to look at, which one of these resonance structures has more contribution and what does that tell us about the structure? So then, which atoms have stronger resonance donors, and then how electron orbitals affect resonance. So it's a lot of resonance today. So like I told you, you never escape. You never escape. Resonance is super, super important. And so that's going to be a lot of what we talk about today. So our learning objectives: identify carboxylic acid derivatives. So there are quite a few of them. And they all react in very similar ways, but not exactly the same. So this is one of those chapters where we are starting to pull together all of the little bits of information that we've been learning over the course of the semester. And we now need to apply that over the course of these carboxylic acid derivatives. If you're one of those people who's been trying to memorize every single reaction, this chapter is going to be hard for you because there are lots of them that are very similar. But if you've been trying to identify the patterns over the course of the semester, this chapter is pretty easy because there's only one reaction. And it's just lots of variations on one reaction. And so it's really, really important to try to break it down into those fundamentals so that it doesn't get overwhelming. Okay, but it should feel very repetitive because it is very repetitive. Okay, so we are going to introduce carboxylic acid derivatives and then their relative reactivity, and then just introduce that one reaction that we're going to talk about over and over and over again. And then the next couple lectures will dig in a lot deeper. So let's start with our first learning objective. So first, we just want to identify carboxylic acid derivatives. And I will often abbreviate that as CAD, carboxylic acid derivatives, because carboxylic acid derivatives is annoying to write out a lot. Okay, so first let's just know what we're looking at. So CAD generally have the form that looks like this, okay? So this red part here, right, is an acyl group. Think about Friedel-Crafts acylation, right? You've seen that motif before, acyl group. And then we have this X group. This X group is going to be some heteroatom such that this carbonyl carbon right there has 3 bonds to heteroatoms. So that carbonyl carbon is in a high oxidation state because it has a lot of carbon oxygen or carbon nitrogen bonds. So this is the same number of heteroatom bonds as carboxylic acids. So that's why they're called carboxylic acid derivatives, because it has the same number of carbon heteroatom bonds. So let's look at some examples of this. I'm going to try to keep this color coding. So we've learned previously about carboxylic acids, right? So like this. So this central carbonyl carbon right there, right, has this double bond to oxygen. So that's 2 bonds to oxygen, and then the single bond to this other oxygen. So we've got 3 CO bonds, right? 3 bonds to heteroatoms. Very similarly to that, instead of OH, we could have OR prime. So O methyl, O ethyl, right? Whatever that R prime group is. So this is going to be an ester. So like that lactide that I showed you before. This also has 3 CO bonds. So we've got 2 bonds to oxygen in the carbonyl, 1 bond to oxygen for this OR group. So those are probably the most straightforward. So then we get into the ones that are a little bit different. So we can have this same acyl group, but now our X group looks a little bit weird in an anhydride. So this is called an anhydride. This is the one that throws people off, I would say. But it's not different. It's just this whole group here in purple is the X group. Okay, don't get confused because it's bigger. It's just an X group. We're still talking about this carbonyl carbon. That carbonyl carbon also has 3 CO bonds. It's not different. Looks kind of weird, but it's not different, I promise. Another one that you've seen previously is where that X is equal to chlorine, right? Again, Friedel-Crafts acylation, right? We use this acid chloride. So in this case, we have 2 CO bonds and 1 CCl bond, but that's still a heteroatom, right? So 2 bonds to oxygen, 1 bond to chlorine, still 3 bonds to heteroatoms. So that's still in the same oxidation state. It's still a carboxylic acid derivative. And then our last kind of normal class are amides. And there are 3 different types of amides just based on the number of substituents. So if we just have NH2 here, that is called a primary amide. But it doesn't have to be NH2. You could have NHR prime. So if that nitrogen has 1 hydrogen and 1 carbon-based substituent, that would be called a secondary amide. Or you can have that nitrogen have 2 R prime groups. So no hydrogens on the nitrogen. And that is called a tertiary amide. So in all of these cases, we're still talking about this carbonyl carbon. We have 2 CO bonds and 1 CN bond. Right? So again, 3 bonds to heteroatoms. So that's how you know that it's a carboxylic acid derivative. Okay. So there is one weird one that doesn't really follow these rules. It still has 3 bonds of heteroatoms. It just looks weird. So the weird one is the nitrile, which looks like this. So this is the nitrile. We have 3 CN bonds. So because we still have 3 bonds to heteroatoms, it is still a carboxylic acid derivative, but it looks real different, right? We don't really have that acyl group. So that one's a little bit weird. We'll kind of treat that one separately, but it does actually react the same way. It just looks weird. Okay, so that's how you know if something is a carboxylic acid derivative, right? Look at that carbonyl carbon. Does it have 3 bonds to heteroatoms? That's going to be a carboxylic acid derivative, as opposed to ketones or aldehydes, which only have 2 bonds to heteroatoms, okay? And they react very differently. So it's really important to differentiate those. Questions on that? It's like, that's super important for like the rest of the lecture. Okay. So now that we know what carboxylic acid derivatives are, we have to start comparing them. So our next learning objective is 20B. Explain CAD reactivity trends, or rank in order of reactivity using resonance arguments. Which is section 20.2. Okay, so we just talked about a bunch of different CADs, right? We have this generic form, acyl X, right? Acyl X. So basically the question is, are all CAD interchangeable? The answer is a big no. They are not interchangeable. And the reason that they are not interchangeable is because of the strength of this bond. Okay, so we need to be able to understand the strength of that CX bond to rationalize the reactivity of these things. So in general, if we have a stronger bond, that gives you a more stable compound. That makes it less reactive. Or vice versa, right? If you have a weaker bond, that's less stable and more reactive, okay? So that's kind of the general trend. More stable bond, more stronger bond, more stable compound, less reactive. So in the learning objective, it says we're going to use resonance arguments. So let's think about the resonance for a second. So in our generic structure, we will do this more specifically in a second. I'm going to draw out my Lewis structure. Because X is a heteroatom, it always has at least one lone pair. So we can draw a resonance structure where we push that lone pair towards that carbonyl carbon, break the pi bond, can draw a resonance structure. Like so. So this is sort of the key resonance structure that we are going to be looking at, where we have this double bond character in that CX bond, okay? So the more double bond character, the stronger the bond, okay? So that's what we're going to be looking at. Please note that there is one other resonance structure. If I were just to pull that electron density back, I could also draw a resonance structure where I put the positive charge on the carbon right here. All right. So that's showing us why that carbon is electrophilic. We'll get to that in a bit. But for now, we're focused on this resonance structure where we have a CX double bond, okay? All right, so let's start with acid chlorides. So for acid chlorides, X equals chlorine. All right, so let's draw out our two resonance structures here. Here's our acid chloride. So our Cl has 3 lone pairs. We can push one of those lone pairs in, like so, to draw our resonance structure, where we have that CX or CCl double bond. All right, so again, this is the one that we care about. So we need to recognize, if we look at our periodic table, right, chlorine is on the second row down, right? So that means that the orbital in which that lone pair is sitting is a 3p orbital, right? We're on the third row down. Whereas for carbon, it would be a 2p orbital, right? Because chlorine is 1 row below carbon. So as we go down the periodic table, those orbitals get much bigger. So we have a small 2p orbital and a large 3p orbital, and they do not overlap very well. Okay, so this has poor overlap. Because it has poor overlap, this resonance structure has very low contribution. So there's not a lot of that double bond character because there's poor overlap, right? So it doesn't want to form that double bond very much. In addition to this poor overlap, we can also think about chlorine is also an electron withdrawing group, a pretty strong one. So it's really making that carbon more electrophilic. So for both of these reasons, acid chlorides are super, super reactive, okay? This is our most reactive CAD, the most reactive one, because we have the lowest double bond character, and chlorine is like a really good leaving group and electron withdrawing. Okay, so highly reactive. All All right, so then let's go to anhydrides. So in anhydrides, that X group is the one that looks weird, right? Sort of has this, almost looks like a carboxylate, right? Okay, so let's draw out our resonance structures again. So don't be afraid that it looks weird. It's just an X group, right? Just attach that whole X group to the acyl. Okay, and then this central oxygen can push its lone pair towards the acyl group. So we form our double bond. This oxygen is now positively charged, right? And we have our CX double bond again, right? So that's the one that we care about. So again, this is the resonance structure we care about. But you'll notice that this starting molecule is symmetrical, right? So we should be able to also draw the resonance structure on the other side. So there's actually one more resonance structure we need to draw, where we push this to the other side, like so. So now, this is the equivalent. These two are equivalent, but we're focusing on the red side on the left. So that's why the blue box one is the one we care about, because it's the one that I'm arbitrarily calling on the red acyl side. Okay, so now let's compare this to the acid chloride. So now it's carbon, oxygen, carbon, oxygen. All of these orbitals that we're talking about are from that second row. So now we have a 2p orbital and a 2p orbital, which is much better, right? Much better overlap. So this is better than our Cl, right? So that means that our boxed resonance structure has a higher contribution. So it's a stronger bond, therefore our reactivity is lower than acid chlorides. Right? So a higher contribution of the boxed resonance structure means lower reactivity. Okay? That's probably the weirdest one, because anhydrides just look weird. Okay, so acid chlorides at the top, then anhydrides. Oops, did not finish writing this. Okay, the next one is esters. So that X group is now OR prime. So that's our ester. We're going to draw a resonance structure again. Going to push the lone pair towards the carbonyl carbon, break the double bond. Okay, so here is our CX bond resonance structure. Okay, so similar to anhydrides, right? We have the 2p orbitals, right? No, nothing's different, right? It's all carbons and oxygens here, so that's fine. But for the anhydrides, right, it has 3 major resonance structures, whereas the ester only has 2 major resonance structures. Because esters only have 2 major resonance structures, this one therefore has a higher percent contribution, because it's not spread out over as many atoms, right? Here we have these electrons spread from this oxygen to this double bond to this double bond. Here we just have it on this oxygen and this double bond. There's no way for it to go in the other direction. Therefore, this box resonance structure has a higher contribution. So that's probably the hardest one to rationalize, right? How many structures are we averaging between? If we are averaging over fewer structures, each of those structures has a higher contribution. Okay? We have more contribution from our double bond resonance structure. Therefore, our reactivity is lower than an anhydride. Okay? Acid chlorides, anhydrides, esters. The last one are the amides, where our X group is going to be our NH2, NHR, NHR2, R2, any of those. Doesn't matter. It's the same. Let's first draw our amide. Nitrogen has a lone pair. Once again, we can draw a resonance structure, push from the lone pair, break the double bond. This is the one that we care about. Okay, so to compare this one to an ester, we're going to think about how nitrogen is less electronegative than oxygen, right? So it's more willing to allow its lone pair into this resonance. Therefore, we have a higher contribution of that boxed resonance structure. Therefore, our reactivity is lower than our ester. So we showed them in order of most reactive to less reactive, sort of kept going down step by step by step. Questions on that? So we expect you to be able to use these resonance arguments to explain why you have different reactivity between all of these different carboxylic acid derivatives. Yes. Yeah, great question. So the question is why does the double bond resonance structure make it less reactive? So the more contribution of the double bond resonance structure means that the actual structure has a stronger bond here, right? And so double bonds are stronger than single bonds, right? And resonance structures means they're not flipping between them. It's the average of all of them, right? So if we have a stronger contribution, the actual structure has more double bond character at this position than this one. And therefore, it's a stronger bond, more stable compound, less reactive. Yeah, great question. Anything else? All right, let's do a chime-in question. Let's see if that's making sense. So there are lots of ways of asking this question. So we might say, which one is the most reactive, which is what this says. It might say, which one is the most stable, which one has the most double bond character. All of those are asking the same question, okay? So this one's asking, which of the following compounds is most reactive? Again, feel free to chat with your neighbors. Maybe 10 more seconds to get your answers in. All right, let's see what we got. Nice, excellent. The acid chloride is the most reactive, right? So make sure that we're reading the question carefully. Most reactive is going to be the acid chloride. If we're asking for the most stable, that would be not that, right? So let's kind of go through this together. So we had an ester, we had an amide, we had an acid chloride, and we had an anhydride, right? So from a reactivity perspective, oops, can't spell, reactivity. Number one is going to be that acid chloride, right? Least double bond character. Then it would be the anhydride, then it would be the ester, then it would be the amide. If the question instead were to ask about stability, the most stable compound would be the amide, followed by the ester, followed by the anhydride, followed by the acid chloride. So they are opposite trends, okay? So again, less reactive equals more stable and vice versa. Okay? Questions on that? Seems like most people are getting it, which is great. Okay? So in addition to knowing about just straight up reactivity, rank them, stability, rank them, this also has implications on what can be interconverted into what. So, oops. So these trends dictate which CAD can be converted to another. So I'm going to make a little bit of a chart. I'm a big chart person to summarize what we just talked about and then explain what I mean by this. Okay, so our summary is acid chlorides at the top, followed by anhydrides, followed by esters, followed by amides. All right, just label them acid chloride, anhydride, ester, amide. Okay, so we said going up this chart, we have our reactivity trend. So the most reactive is at the top. Oops, reactive. Okay. Going down this chart, we have our stability, where our most stable is at the bottom. Another way to think about this is as we go up this chart, we have leaving group ability, right? So like Cl minus is happier than our carboxylate, which is happier than an alkoxide, which is happier than an amide, right? So the better the leaving group, the more reactive it is, right? All of those things are related. Okay, so then what does this mean about which CAD can be converted into each other? So any CAD can be converted to another below it on this chart. Right? So you always have to go from more reactive to less reactive. So you can convert an acid chloride into an anhydride, but not vice versa. Okay, so we always have to be going down this chart. You cannot go in the opposite direction. So if you start from an amide, you cannot use like a chloride nucleophile to go back up to an acid chloride. You can't do that, okay? So that's really, really important when thinking about this, is like, what direction are we moving on this chart? And making sure that we're always going to the more stable direction. Questions on that? Yes?
Is there any significant difference in the reactivity between primary, secondary, tertiary?
Yeah, that's a great question. So the difference between primary, secondary, and tertiary amides. So technically, yes. So a primary amide is more reactive than secondary and more reactive than tertiary. But like in this context, no. All the amides are still at the bottom of the chart. Other questions? Okay, so that's your crash course into carboxylic acid derivatives. Okay, so now we are going to introduce the one reaction that we're going to be talking about for the next, like, I don't even know how many lectures, at least 2, maybe 3. It's just one reaction. There's just lots of variations on this reaction. Okay, so we're going to start a new one. So learning objective 20C. Right now, we just want you to be able to recognize a nucleophilic acyl substitution, which is 20.3. And we will get into the nitty-gritties of nucleophilic acyl substitutions for each of these carboxylic acid derivatives. But for today, we're going to do a very generic mechanism. And then as we go through the specifics, you'll start to see how they're slightly different from each other, but they're essentially the same. Okay, so the general like scheme of this reaction is that you have some sort of carboxylic acid derivative, right? So here's our CAD, and you're going to react it with a nucleophile, right? Nucleophilic acyl substitution. So we need a nucleophile. So that could either be, you know, nucleophilic H, or it could be a negatively charged nucleophile. That can change the mechanism a little bit, but basically the same. That will replace our X group, substitute our X group with the nucleophile. Okay, so whatever our nucleophile is now bound to that carbonyl carbon. And then our X group has left, either as HX or X minus, depending on the conditions. So this is a nucleophilic acyl substitution. You start with a carboxylic acid derivative. You usually end with a carboxylic acid derivative, not always, but usually. And you replace the X group with the nucleophile. Okay, that's it. Replace the X group with the nucleophile. And so we will get into the differences. So there's a slightly different mechanism depending on our carboxylic acid derivative and what your nucleophile is. But it's mostly basic conditions or acidic conditions, right? Like which one are you using? Okay, so what can the nucleophile be? So negatively charged nucleophiles that are common would be like sodium ethoxide, right? So that ethoxide is a negatively charged nucleophile. Or sodium hydroxide, right? Those are negatively charged nucleophiles. Similarly, sodium carboxylate. Something like that. But it could also be, so all of those would give carboxylic acid derivatives as their products. So either a carboxylic acid or an ester or an anhydride. But it doesn't have to be. It could be a Grignard, right? So organometallics, where you're basically thinking about it as carbon minus, right? Super, super strong nucleophiles, very basic conditions. In this case, though, this will result in like a ketone or an alcohol, not a CAD, because we're making a carbon-carbon bond, so we no longer will have 3 bonds to heteroatoms. Okay, so we'll go a bit more into that, but I just wanted to put that on your radar, that nucleophilic acyl substitutions are defined by their starting materials, not their products. because you can get a bunch of different products depending on what your nucleophile is. Examples of protonated nucleophiles, right? So nucleophilic with an H would be like an amine. So here's diethylamine, for example. That would give you an amide. Or it could be methanol plus acid. So you'll see that we can do some of these under either acidic or basic conditions, and others are only basic conditions. And so we will differentiate those as we go. So those are some examples of what is to come. I promise that we will get much farther into it as we go. All right. So before we get into all the specifics, let's just do a generic mechanism. I would like you to try and translate this generic mechanism onto every reaction we do in this chapter, okay? Every single one. If you're trying to do them separately, it's gonna get real rough for you, but I promise you they are all the same. So let's go through the general mechanism first. All right, so we have heard of these before, and it is called an addition-elimination mechanism. That means it must have at least 2 steps, right? You must have at least one addition and at least one elimination. Those cannot happen in the same step. They must be different steps. Sometimes we'll have more than that, but we need at least those 2 steps. You've seen this before in nucleophilic aromatic substitution, way back in chapter 13, also an addition-elimination mechanism, okay? All right, so generically, we have some carboxylic acid derivative. And we have some nucleophile. I'm going to use nucleophile minus because we're just doing a very simple mechanism to start. Okay. Addition means that our nucleophile attacks our electrophile and we break the weakest bond, like every other reaction we have been learning. Okay. So our nucleophile, right, is where the negative charge is. Always start the arrow pushing from the lone pair. Our electrophilic site is that carbonyl carbon, right? We have that partial positive charge there. Nucleophile attacks electrophile, break the pi bond. This is our addition step because we've added the nucleophile. What does that give us? That gives us okay. Our X group is still attached and our nucleophile is also attached. So that carbonyl carbon is right here. Notice that our carbonyl carbon has gone from an sp2 hybridized carbon to an sp3 hybridized carbon, right? So this was sp2, now it's sp3. And remember that sp3 carbons have a tetrahedral kind of geometry. So we call this our tetrahedral intermediate. So you've learned that before with ketones and aldehydes, similar thing, right? Ketones and aldehydes, that carbon starts as sp2, you add something to it, it becomes sp3, that's a tetrahedral intermediate. Same thing here, okay? We have our tetrahedral intermediate, and our X group is our leaving group, right? We said that the reactivity trends with the leaving group ability of X. So that means X is our leaving group. It's always our leaving group, okay? So now we need to do our elimination step. So elimination, what are we eliminating? The leaving group, okay? So we need to collapse the tetrahedral intermediate, which means that we push our lone pairs down to reform our double bond, and our leaving group leaves. So this is our elimination step. So what have we done? We have remade our carbonyl, but now instead of having a bond to X, we have a bond to the nucleophile. And our X has left, in this case, as X minus. That's it. That's the general mechanism that every reaction is going to have. Nucleophile attacks the carboxylic acid derivative, forms a tetrahedral intermediate, collapse the tetrahedral intermediate, leaving group leaves. Okay? Those 2 steps are going to exist in every single reaction. Every single nucleophilic acyl substitution has those 2 steps. The only ones that kind of are on top of that are proton transfers. Yes?
If there was added acid in solution, would it form the OH and would the lead group still lead?
It's a great question. We will get into that. That's like the next 2 lectures is all about that. So I promise we will get more into that. I just want to introduce the general concept first, but acid is a little bit more complicated. You're right. Okay, let's give like just a generic actual example so that it's not just with X's and nucleophile. So here's an example with an acid chloride and say sodium acetate. Okay. So 4 P's, right? I pick out your nucleophile. That better be where the negative charge is, right? So one of these lone pairs on our carboxylate is going to be our nucleophile. In all of these reactions, when you pick out your electrophile, it better be the carboxylic acid derivative carbonyl carbon every single time. Okay? Every single time. Nucleophile attacks electrophile, break the weakest bond. That's our addition step. Form our tetrahedral intermediate. Okay, so this is our tetrahedral intermediate, right? That central carbonyl carbon is right here. It's attached to what was our carbonyl oxygen, our leaving group, which is the chlorine, and our nucleophile, which is the carboxylate. Then we need to collapse the tetrahedral intermediate. Leaving group leaves. This is our elimination step. So overall, we end up with an anhydride, and sodium chloride is our byproduct here. So in this case, right, we started with a carboxylic acid derivative. This is our acid chloride. We end up with an anhydride, another carboxylic acid derivative. We consult our chart, make sure that we're going down the chart, which we are, right? Acid chloride can go to anhydride, that's fine. So why not backwards? So I like to just point this out. So why not backwards? Because you could draw a mechanism that goes from the anhydride back to the acid chloride, right? But let's look at this tetrahedral intermediate here, right? At this stage, we need to collapse our tetrahedral intermediate. Which one is going to leave? The chlorine or the carboxylate? The one that's easier to leave is the chlorine. That's why it's going to drive it in this direction. You can't go backwards because there's no way that this one is going to want to leave more than that chlorine, right? So it's all about that leaving group ability once you get to this tetrahedral intermediate, because now it has 2 choices. It's always going to choose the choice where it makes the more stable thing, right? And so that's kind of how we can figure it out. So we want to look here, which is the better leaving group. And in this case, it's going to be chlorine minus. And so that's why we're going to go in that direction, okay? All right, that's our generic nucleophilic acyl substitution mechanism. I'm going to stop there today. We're going to do a bunch of versions of this on Friday and Monday for sure.